The universe just broke its own rules. A single galaxy shooting plasma beams across 23 million light-years, so far that our entire cosmic neighborhood fits in a fraction of its length. Theory said this couldn't happen. Reality had other plans. And here is a question. If you could discover one thing about the universe that scientists haven't figured out yet, what would it be? Let us know in the comments. I will pin the most creative answer. Now let's begin. When you look up at the night sky, you're seeing photons that have traveled across unimaginable distances to reach your eyes. Light from Proxima Centauri, our nearest stellar neighbor, takes over 4 years to arrive. Light from Andromeda, the closest major galaxy to ours, has been journeying through the void for 2.5 million years. But the galaxies we're about to explore, their light has been traveling for billions of years, crossing distances so vast that our minds struggle to grasp them. For decades, astronomers thought they understood the upper limits of galactic size. Sure, galaxies came in different shapes and masses, from tiny dwarf galaxies containing just a few billion stars to massive elliptical giants housing trillions. But there seemed to be a ceiling, a cosmic speed limit on how large a single galaxy could grow. Then we developed better telescopes. We learned to see in wavelengths invisible to human eyes, and what we found shattered every assumption we'd made. The story begins with a galaxy called IC 1101. Nestled in the heart of the Abell 2029 galaxy cluster, over 1 billion light-years from Earth, IC 1101 held the record for decades as the largest known galaxy by stellar mass and physical extent. Picture this: a galaxy containing somewhere between 10 trillion and 100 trillion stars. That's roughly 1,000 times more stars than our entire Milky Way possesses. Its visible body stretches across an astounding 4 million to 6 million light-years, while its faint outer halo extends even further, creating a gossamer envelope of ancient stars that pervades the space between galaxies. To put that in perspective, our Milky Way measures approximately 100,000 light-years across. Andromeda, our larger neighbor, spans about 220,000 light-years. IC 1101 could swallow both of them, along with every other galaxy in our local group, and still have room to spare. At its heart lurks a supermassive black hole weighing in at somewhere between 40 billion and 100 billion times the mass of our Sun. This cosmic monster sits relatively quiet now, but its past feeding frenzies helped sculpt the galaxy into the behemoth we observe today. IC 1101 represents what astronomers call a brightest cluster galaxy, or BCG for short. These galactic titans sit at the centers of massive galaxy clusters, where they've grown fat by cannibalizing their neighbors over billions of years. Every time a smaller galaxy wanders too close, the gravitational embrace of the BCG strips away stars, gas, and dark matter, adding them to its ever-growing mass. It's cosmic cannibalism on a scale that defies imagination. But here's where the story takes a fascinating turn. In February 2022, a team of astronomers led by Martijn Ooi at Leiden University in the Netherlands made an announcement that would rewrite our understanding of galactic megastructures. Using data from the Low Frequency Array, or LOFAR, a network of radio telescopes spread across Europe, they discovered something extraordinary lurking in the constellation Lynx, approximately 3 billion light-years from Earth. They named it Alcyoneus, after the giant from Greek mythology who challenged the gods themselves. And challenging is exactly what this discovery did to our assumptions about cosmic scale. Alcyoneus isn't remarkable for its stellar mass or the number of stars it contains. In fact, by those metrics, it's fairly ordinary for a large galaxy. What makes Alcyoneus absolutely jaw-dropping is the structure extending from its core. Two enormous jets of plasma launched by the supermassive black hole at the galaxy's heart stretch out into intergalactic space for a mind-bending 16 million light-years. That's roughly 160 times the diameter of our Milky Way. If you could somehow place Alcyoneus where our galaxy sits, one jet would extend past the Virgo supercluster, while the other would reach in the opposite direction across an equivalent distance. I know what you might be thinking. How can a galaxy be 16 million light-years across? Don't galaxies have, edges? And you'd be absolutely right to question that. The stellar body of Alcyoneus, the part containing visible stars, measures a relatively modest 243,000 light-years across. Impressive, but nowhere near record-breaking. What creates that staggering 16 million light-year measurement are the radio lobes, massive structures of superheated plasma ejected by the central black hole and traveling at nearly the speed of light. The discovery of Alcyoneus wasn't the end of the story, it was just the beginning. Because in September 2024, the same research team, still led by Martin Oey but now working at Caltech, announced they'd found something even larger. They called it Porphyrion, after another giant from Greek mythology who fought alongside Alcyoneus against the Olympian gods. Porphyrion sits an astounding 7.5 billion light-years away from us. Its light began the journey to Earth when the universe was roughly half its current age. And stretching out from this distant galaxy are two jets spanning 23 million light-years across. Let me say that again, 23 million light-years. That's 230 times the width of the Milky Way. 140 Milky Way galaxies could line up end-to-end within Porphyrion's reach. But wait, because the story doesn't end there either. Shortly after Porphyrion's discovery, astronomers identified yet another radio galaxy designated TXS 003 3+252 with an estimated extent of 26 million light-years. The race to find the largest structures in the universe continues, and every new discovery forces us to reconsider what we thought we knew. So what exactly are these cosmic giants? How can a single galaxy create structures that dwarf entire galactic clusters? The answer lies in one of the universe's most extreme phenomena, supermassive black holes and the relativistic jets they produce. If you're enjoying this deep dive, make sure to give this video a like and hit that subscribe button. It really helps the channel grow, and I've got so much more cosmic content coming your way. At the center of nearly every large galaxy lurks a supermassive black hole containing anywhere from millions to billions of times the mass of our Sun. These aren't the stellar mass black holes formed when massive stars collapse. Supermassive black holes are fundamentally different beasts, likely formed in the chaotic early universe through mechanisms we're still trying to understand. They grow by devouring everything that ventures too close: gas, dust, entire stars, even other black holes. But here's the paradox that puzzled astronomers for decades. Black holes are supposed to be cosmic vacuum cleaners, pulling matter in and never letting it escape. Yet some of the brightest objects in the universe are powered by black holes. How can something from which not even light can escape become one of the most luminous phenomena we observe? The answer involves one of nature's most elegant feedback mechanisms. When material spirals toward a supermassive black hole, it forms what we call an accretion disk, a swirling maelstrom of superheated matter orbiting at significant fractions of light speed. Friction within this disk heats the material to millions of degrees, causing it to emit tremendous amounts of radiation across the electromagnetic spectrum. But not all of this material makes it past the event horizon. Some of it gets caught up in the black hole's powerful magnetic fields, which act like cosmic particle accelerators. These magnetic fields, twisted and amplified by the rotation of the black hole and its accretion disk, channel a fraction of the infalling material into two narrow jets perpendicular to the disk. The particles in these jets get accelerated to 99.9% of light speed or faster, creating beams of energy that lance through space for distances that make interstellar space look microscopic. When electrons in these jets spiral around magnetic field lines, they emit synchrotron radiation, which we detect as radio waves here on Earth. This is what we're actually seeing when we observe galaxies like Alcyoneus and Porphyrion with radio telescopes. The LOFAR array, operating at frequencies between 10 and 240 MHz, is specifically designed to detect these long wavelength radio emissions. At these frequencies, the radio lobes glow brilliantly, revealing structures completely invisible to optical telescopes. You could point the Hubble Space Telescope directly at Porphyrion and see nothing but a faint smudge where the host galaxy sits. But switch to radio wavelengths and suddenly you're looking at one of the largest single structures in the observable universe. Now these radio galaxies challenge something fundamental about our understanding of cosmic evolution. For the jets to maintain their coherence across such enormous distances requires very specific conditions. The intergalactic medium, that thin soup of gas and plasma filling the space between galaxies, can't be too dense, or it would disrupt the jets. The black hole needs to maintain a relatively steady rate of accretion over millions of years to keep the jets powered, and the host galaxy needs to exist in a cosmic environment that allows this kind of expansion. Scientists estimate that Porphyrion's jets have been active for approximately 1 billion years. Think about that for a moment. When these jets first ignited, Earth was in the Neoproterozoic era, when the most complex life consisted of simple, multicellular organisms. The jets have been continuously blasting plasma into intergalactic space for longer than animals have existed on our planet. And remember, we're seeing Porphyrion as it was 7.5 billion years ago, when the universe itself was barely 6 billion years old. This raises a question that keeps cosmologists awake at night. If structures this large existed when the universe was relatively young, what does that tell us about the conditions in the early cosmos? The prevailing models suggested that the intergalactic medium in the younger universe should have been denser, more turbulent, making it harder for jets to propagate across such vast distances. Yet here's Porphyrion, defying those expectations, its jets reaching across a significant fraction of what we call a cosmic void. Speaking of cosmic voids, let me paint you a picture of the universe's large-scale structure. If you could zoom out far enough to see billions of light years in all directions, you'd notice that galaxies aren't randomly distributed through space. Instead, they cluster together along filaments, creating a cosmic web of matter separated by enormous voids containing very few galaxies. These voids represent the largest empty spaces in the universe, typically spanning 60 to 150 million light-years across. Porphyrion's jets span roughly 23 million light-years, which represents approximately 60 to 70% of the radius of a typical cosmic void in today's universe. But here's the mind-bending part. When Porphyrion's jets were active, cosmic voids were smaller because the universe itself was smaller. At that epoch, Porphyrion's reach represented an even larger fraction of the void radius, meaning these jets could potentially influence the structure of matter on scales approaching the cosmic web itself. This discovery has profound implications for something called cosmic feedback. For years, astronomers have known that supermassive black holes influence their host galaxies through various feedback mechanisms. The energy pumped out by active black holes heats the surrounding gas, preventing it from cooling and collapsing to form new stars. This is why the most massive elliptical galaxies appear red and dead, containing primarily old stars with very little ongoing star formation. The black holes at their centers have essentially shut down the star-making process. But if jets like Porphyrion's can reach across such enormous distances, they're not just affecting their host galaxies, they're potentially influencing the evolution of neighboring galaxies, heating the intergalactic medium across volumes of space containing thousands of galaxies. They're seeding the cosmic web with magnetic fields and cosmic rays, potentially affecting how matter clumps together under gravity to form the large-scale structures we observe. This brings me to something I find deeply fascinating. You know what really puts these discoveries in perspective? Understanding just how isolated we might be in this vast cosmos. The distances we're talking about with these giant radio galaxies make the Fermi paradox even more haunting. If you want to explore why the universe makes it nearly impossible for any two civilizations to ever meet, I actually made a video about that called Why the Universe Makes It Impossible for Any Two Civilizations to Ever Meet. It explores the terrifying math behind cosmic distances and why we might be far more alone than we'd like to believe. You should definitely check it out after this one, but let's get back to our cosmic giants. The discovery of these massive radio galaxies also tells us something profound about the history of black hole activity in the universe. Not all supermassive black holes produce these dramatic jets. In fact, most don't, or at least not continuously. Our own Milky Way's supermassive black hole, Sagittarius A star, weighing in at about 4 million solar masses, is relatively quiet right now. It occasionally flares up when it devours a passing gas cloud or unlucky star, but it's not producing the kind of sustained jet activity we see in radio galaxies. The question that naturally arises is why some black holes produce these enormous jets while others don't. The answer involves a complex interplay of factors that we're still working to fully understand. Black hole spin appears to play a crucial role. According to our best models, the most powerful jets emerge from rapidly spinning black holes, where the rotation helps generate and amplify the magnetic fields that launch the jets. But spin alone isn't enough. You also need a steady supply of fuel, meaning gas and matter need to be funneling toward the black hole at just the right rate. Feed a black hole too quickly, and the infalling material can actually choke off the jets through a process we don't entirely understand yet. Feed it too slowly and you won't generate the energy needed to create and sustain these massive structures. The sweet spot seems to involve moderate feeding rates sustained over incredibly long timescales. This is where galaxy mergers come into play. When two galaxies collide and merge, the process funnels enormous amounts of gas toward the central regions, where it can feed the supermassive black holes. Many of the giant radio galaxies we've discovered appear to be associated with galaxy mergers or exist in environments where they're actively consuming smaller satellite galaxies. But here's where things get really interesting and where our understanding starts to hit its limits. The host galaxy of Porphyrion, designated with the wonderfully catchy name J15293.2.1 plus 6 0 1534.4, appears relatively ordinary. It's not an obvious mega-merger. It's not sitting at the center of a dense galaxy cluster where you'd expect lots of interactions. By most metrics, it looks like a fairly normal massive elliptical galaxy, yet somehow its central black hole has generated the largest known structure created by a single galaxy. This challenges some long-held assumptions. For years, astronomers theorized that giant radio galaxies could only grow to certain sizes before environmental factors would disrupt their jets. Dense intergalactic medium would slow them down. Interactions with other galaxies would bend or break them. Instabilities within the jets themselves would cause them to dissipate. These theoretical limits suggested a maximum size of around 5 million light-years for radio galaxy lobes. Then Alcyoneus came along at 16 million light-years. Then Porphyrion at 23 million light-years. Then TXS 0033 plus 2, 52 at 26 million light-years. Each discovery pushes the boundaries further, forcing theorists back to their models to figure out what they're missing. And this is precisely how science advances. We make predictions based on our current understanding. Nature reveals something that doesn't match those predictions. We revise our models and try again. It's a humbling process, and it reminds us that despite all our technological sophistication and mathematical prowess, the universe still has the power to surprise us. Let me share something that really drives home the scale we're dealing with. Light travels at 299,792,458 meters per second. Nothing in the universe moves faster. At this speed, light can circle Earth's equator 7.5 times in a single second. It takes light just 1.3 seconds to travel from Earth to the Moon, 8 minutes and 20 seconds to reach us from the Sun. Yet it would take light 23 million years to traverse Porphyrion from one end of its jets to the other. Imagine you're a photon of light emitted from one lobe of Porphyrion and traveling toward the other lobe. When you begin your journey, Earth is in the Miocene epoch. The continents have nearly reached their modern positions, but the land bridge between North and South America hasn't formed yet. The ancestors of humans are small, tree-dwelling primates. You race across the void at the ultimate cosmic speed limit, never slowing, never stopping. You pass through the host galaxy and out the other side. You continue across vast stretches of intergalactic space, occasionally passing lonely galaxies drifting in the darkness. 23 million years later, when you finally reach the far lobe, Earth has transformed beyond recognition. Grasslands have spread across continents. Ice ages have come and gone. A lineage of African apes has evolved consciousness, looked up at the stars and begun to wonder about their place in the cosmos. That's the timescale we're talking about. And remember, these jets aren't static structures. They're dynamic, constantly being fed by fresh material from the central black hole, with the leading edges plowing through the intergalactic medium like a snowplow pushing through fresh powder. The energy required to maintain these structures is staggering. We're talking about outputs equivalent to billions of suns shining continuously for millions of years. Now, you might be wondering how we actually measure these distances. After all, when you're looking at an object billions of light years away, you can't exactly pull out a cosmic tape measure. The process involves some elegant astronomy and physics. First, we determine the galaxy's redshift by analyzing its light spectrum. As the universe expands, space itself stretches, and this stretching affects light traveling through it. Light from distant galaxies gets shifted toward longer, redder wavelengths. The amount of this redshift tells us how much the universe has expanded since the light was emitted, which in turn tells us how far away the galaxy is and how long ago we're seeing it. For Porphyrion, the redshift is 0.896, which corresponds to a light travel time of approximately 7.5 billion years. But here's a subtle point that trips people up. That doesn't mean Porphyrion is 7.5 billion light years away. Because the universe has been expanding this whole time, the galaxy is actually much farther away now than it was when the light we're seeing was emitted. Taking cosmic expansion into account, Porphyrion currently sits approximately 10.3 billion light years from Earth, though of course we're seeing it as it was 7.5 billion years ago. We have no idea what it looks like right now at this very moment. Once we know the distance, we can use the apparent angular size of the radio lobes to calculate their physical extent. It's the same principle you use when you hold your thumb at arm's length to estimate the size of a distant object. If you know how far away something is and you can measure the angle it takes up in your field of view, basic geometry gives you its actual size. The radio telescopes of LOFAR can resolve structures down to a few arcseconds, which is crucial for mapping these enormous but extremely faint radio lobes. And faint is putting it mildly. The radio emission from these lobes is incredibly weak, by the time it reaches Earth. We're talking about receiving power on the order of 10 to the negative 26 watts per square meter per hertz of bandwidth. To put that in perspective, the total energy collected by all the radio telescopes humanity has ever built, from all cosmic sources combined, wouldn't be enough to melt a single snowflake. This is why we need enormous radio telescope arrays like LOFAR, which combine signals from thousands of individual antennas spread across multiple countries to achieve the sensitivity required to detect these whisper-quiet cosmic giants. The LOFAR array itself is a marvel of modern astronomy. Unlike traditional radio telescopes with large moving dishes, LOFAR consists of thousands of simple antenna stations distributed across Europe, with the densest concentration in the Netherlands. The stations in the Netherlands alone cover an area roughly 100 kilometers across. By combining the signals from all these widely separated antennas through a process called interferometry, LOFAR can achieve resolution comparable to a single telescope the size of the entire array. It's like having a radio telescope the size of a small country. Operating at low frequencies between 10 and 240 megahertz, LOFAR is specifically designed to detect the kind of synchrotron radiation emitted by these ancient, stretched-out radio lobes. Higher frequency observations tend to highlight the bright, compact cores of radio galaxies, but it's at these lower frequencies where the diffuse, extended structures really shine. This is why LOFAR has been so successful at discovering giant radio galaxies. It's looking in exactly the right part of the electromagnetic spectrum with exactly the right combination of sensitivity and resolution. The LOTSS project, or LOFAR 2-meter sky survey, has been systematically mapping the northern sky at these low frequencies, and it's revolutionizing our understanding of radio galaxies. Before LOTSS, we knew of only a few hundred giant radio galaxies. The survey has already discovered hundreds more, and we've barely scratched the surface of the data. Each new data release reveals structures that had been hiding in plain sight, too faint or too extended for previous surveys to detect. What's particularly exciting is that many of these discoveries come from reprocessing existing data with new techniques. Alcyoneus, for instance, wasn't found by pointing telescopes at a new patch of sky. The data had been sitting in archives, but the radio lobes were so faint and spread out that they'd been missed during initial analysis. Martijn Oy and his team developed new image processing algorithms specifically designed to detect these ultra-diffuse structures, and suddenly there was Alcyoneus, the largest known galaxy at the time, hiding in data that had already been publicly available. This tells you something important about modern astronomy. We're not just limited by our telescopes anymore, we're also limited by our ability to process and analyze the tsunami of data those telescopes produce. The square-kilometer array, currently under construction in South Africa and Australia, will generate more data in a single day than the entire internet currently contains. Finding the needles in that haystack will require artificial intelligence, machine learning, and algorithmic innovations we haven't even conceived of yet. But let's return to our giant radio galaxies and explore what they're actually doing to the universe around them. These jets aren't just impressive to look at. They're having profound effects on cosmic evolution. As the jets plow through the intergalactic medium, they create enormous bubbles of hot, shock gas. The leading edges of the jets, where they slam into the surrounding medium, form what we call hot spots, regions where particles are being accelerated to extreme energies and the magnetic fields reach their maximum strength. Behind these hotspots, the jets inflate lobes of relativistic plasma that can persist for hundreds of millions of years, even after the jets themselves shut off. These lobes act like cosmic heating pads, pumping energy into the intergalactic medium and preventing it from cooling down. Cool gas is what you need to form stars. Keep the gas hot and star formation grinds to a halt. This is one of the key mechanisms by which supermassive black holes regulate galaxy growth. But with jets like Porphyrions, this regulation isn't just happening within the host galaxy, it's happening across volumes of space containing potentially thousands of other galaxies. Think about the implications. A single supermassive black hole sitting in a galaxy billions of light-years away can influence whether stars form in galaxies separated from it by distances equivalent to a significant fraction of a cosmic void. It's a form of action at a distance that would have seemed absurd just a few decades ago. There's also the question of magnetic fields. The jets carry strong magnetic fields with them as they expand into intergalactic space. The intergalactic medium was thought to be only weakly magnetized, with magnetic field strengths billions of times weaker than Earth's. But jets like these could be seeding magnetism throughout the cosmic web, potentially influencing how gas collapses to form new galaxies and affecting the propagation of the highest energy cosmic rays that zip through the universe. Cosmic rays, for those unfamiliar, are high-energy particles, mostly protons, that travel through space at nearly the speed of light. The most energetic cosmic rays possess energies that make our most powerful particle accelerators look like children's toys. A single cosmic ray proton detected in 1991, dubbed the "Oh my God" particle, carried energy equivalent to a baseball traveling at 100 kilometers per hour, except all that energy was concentrated in a single subatomic particle. We still don't know for certain where these ultra-high energy cosmic rays come from, but giant radio galaxies are prime suspects. The jets and lobes of radio galaxies are natural particle accelerators, capable of boosting particles to tremendous energies through various mechanisms. As these particles escape from the lobes and diffuse into the broader intergalactic medium, they could account for at least some of the cosmic rays we detect. If Porphyrion-sized jets existed throughout cosmic history, they could have contributed significantly to the cosmic ray background, potentially affecting everything from galaxy formation to the chemistry of the intergalactic medium. Now let's talk about something that might seem contradictory at first. Despite their enormous size, these giant radio galaxies are actually quite rare. Current estimates suggest that only about 10% of massive galaxies go through a radio-loud phase where they produce significant jets. Of those, only a small fraction develop into giant radio galaxies spanning megaparsecs of space. This rarity actually makes them more valuable as cosmic laboratories. They represent extreme conditions, edge cases where the usual rules get pushed to their limits. Scientists love edge cases because they reveal physics that might remain hidden under more typical circumstances. When you push systems to extremes, subtle effects become obvious. Rare conditions create opportunities to test theories in regimes where small differences in the underlying physics produce dramatically different outcomes. This is why discovering galaxies like Porphyrion isn't just about setting records. It's about finding natural experiments that the universe has set up for us, if we're clever enough to recognize and study them. Consider what Porphyrion tells us about black hole spin. To maintain jets over the timescales required to build 23 million light-year structures requires extraordinary stability in the central engine. The black hole needs to maintain its spin axis in the same direction for hundreds of millions to billions of years. This seems straightforward until you remember that supermassive black holes grow by accreting matter and merging with other black holes. Each accretion event, and especially each merger, can potentially change the black hole's spin direction. The fact that we see these beautifully aligned, coherent jets stretching across such vast distances suggests that either these black holes haven't undergone major mergers recently, or there are mechanisms that preferentially align the spin of merging black holes that we don't fully understand yet. Either possibility has important implications for our models of galaxy evolution and black hole growth. It's these kinds of puzzles that keep astrophysicists employed and perpetually fascinated. There's also a selection effect we need to consider. When we observe a radio galaxy, we're seeing it at one particular moment in its life cycle, or rather, one particular moment as it was billions of years ago. We're essentially looking at a single snapshot of a process that unfolds over cosmological timescales. Porphyrion's jets might have been active for 1 billion years, but how much longer will they last? Have they already shut off, and we're seeing the afterglow of a process that ended millions of years ago? Or are they still going strong, continuing to push outward into intergalactic space even as we observe their ancient light? This is one of the fundamental challenges of astronomy. We can't watch individual galaxies evolve in real time because the timescales involved dwarf human lifespans by factors of millions or billions. Instead, we have to observe many different galaxies at different stages of their evolution and piece together the story like assembling a flipbook animation from randomly selected frames. Statistical studies of large samples help, but there's always uncertainty when you're trying to reconstruct a billion-year process from snapshots. What we can say is that the jets probably won't last forever. Eventually, the fuel supply will run out, either because the black hole has consumed all the available gas, or because some other process cuts off the supply. Galaxy mergers, while they can initially trigger black hole activity by funneling gas toward the center, can also disrupt the accretion disk and shut down the jets. Interactions with the intergalactic medium could eventually slow or deflect the jets, causing them to fade or bend. The jets might even become unstable and break up through internal processes we don't yet fully understand. When the jets do finally shut off, the radio lobes don't immediately disappear. They contain enormous amounts of energy stored in relativistic particles and magnetic fields. This energy will slowly radiate away, causing the lobes to fade over tens to hundreds of millions of years. During this fading phase, the lobes continue to heat the surrounding medium and affect their cosmic neighborhood, even though the central engine has gone quiet. Eventually, the lobes will dissipate entirely, their energy transferred to the intergalactic medium, leaving behind only subtle traces in the temperature and magnetization of intergalactic space. But here's something that gives me chills every time I think about it. Right now, at this very moment, there could be radio galaxies forming jets even larger than Porphyrions. They could be out there, actively growing, their jets pushing ever outward into cosmic voids. But we can't see them yet. Either they're so distant that their light hasn't reached us, or they're oriented in such a way that our current surveys haven't detected them, or they're emitting at frequencies we haven't yet surveyed with sufficient sensitivity. The universe is approximately 13.8 billion years old. The most distant objects we can observe had their light emitted when the universe was only a few 100 million years old. There's a whole volume of space beyond what we can currently see, hidden behind the cosmic horizon, forever beyond our observational reach, due to the finite speed of light and the expansion of the universe. What wonders exist in that unreachable realm? What structures dwarf even Porphyrion, existing in a portion of the universe we'll never be able to observe? This brings us to a profound philosophical point about astronomy and the human quest for knowledge. We are, by the very laws of physics, limited in what we can know about the universe. There are questions we can never answer with certainty because the evidence exists beyond our cosmic horizon. There are structures we'll never see because their light will never reach us. And yet we keep looking. We keep building better telescopes, developing more sensitive detectors, creating more sophisticated analysis techniques. Why? Because the alternative, accepting ignorance without pushing against its boundaries, is antithetical to the human spirit. Every time we discover something like Porphyrion, we're reminded that the universe is larger, stranger, and more magnificent than we imagined. These discoveries don't just expand our knowledge, they expand our sense of wonder. They remind us that despite thousands of years of studying the heavens, we're still cosmic novices, barely beginning to grasp the full scope and complexity of the reality we inhabit. Let's zoom out for a moment and consider where these giant radio galaxies fit into the broader cosmic story. The universe began 13.8 billion years ago in an event we call the Big Bang. For the first few 100 million years, the cosmos was a relatively simple place. Hydrogen, helium, a trace of lithium, and dark matter clumping together under gravity. The first stars formed, lived brief, violent lives and exploded, seeding space with heavier elements. The first galaxies assembled from smaller proto-galactic fragments, merging and growing through a hierarchical process that continues to this day. Somewhere along the way, supermassive black holes appeared. We're still not entirely sure how. Did they form from the direct collapse of massive gas clouds in the early universe? Did they grow from seed black holes left behind by the first generation of stars? Did they emerge from the merger of many smaller black holes in dense stellar clusters? Probably all of these mechanisms played roles to varying degrees. What we do know is that by the time the universe was less than 1 billion years old, supermassive black holes containing billions of solar masses already existed, powering quasars so bright we can see them from across the observable universe. These early black holes seem to have been particularly active, accreting material at prodigious rates and shining with luminosities that dwarf entire galaxies. As the universe aged and evolved, this furious activity mellowed. Black holes grew larger but became less active on average. The peak of black hole activity occurred when the universe was between 2 and 4 billion years old, an epoch we call cosmic noon. This is when star formation rates were at their highest, when galaxy mergers were more common, when the universe was a more violent and energetic place than it is today. Porphyrion's jets were active during this era, or perhaps shortly after. The light we see was emitted when the universe was approximately 6 billion years old, well past cosmic noon, but still a time when black hole activity was much more common than today. This raises a tantalizing question. Were giant radio galaxies more common in the earlier universe? If so, they could have played a significant role in shaping cosmic evolution, heating the intergalactic medium and suppressing star formation across vast volumes of space. Some theoretical models suggest that feedback from radio galaxies might help explain a long-standing puzzle in cosmology. When we count up all the stars that should have formed based on the amount of matter in the universe and the laws of gravity, we get a number significantly higher than the number of stars we actually observe. Something has been suppressing star formation, preventing a large fraction of the universe's ordinary matter from collapsing into stars. Supernova explosions provide some of this feedback, but they primarily affect individual galaxies. Radio galaxy jets, especially the giant ones like Porphyrion, could provide the missing piece, operating on much larger scales to heat the intergalactic medium and prevent cosmic gas from cooling and collapsing. Testing this hypothesis requires understanding how common these giant radio galaxies were throughout cosmic history and how much energy they collectively pumped into the universe. This is where surveys like LOTSS become crucial. By cataloging giant radio galaxies across a range of cosmic epochs, astronomers can build up statistical samples large enough to estimate their overall impact. Early results suggest that giant radio galaxies could indeed be significant contributors to cosmic feedback, though we need larger samples and more detailed modeling to be certain. There's another aspect of these discoveries that deserves attention: the sheer detective work involved in finding and characterizing these objects. When Martin Oey and his colleagues discovered Porphyrion, they didn't just process the radio data. They had to cross-reference multiple astronomical catalogues to identify the host galaxy, confirm its distance through spectroscopic observations, rule out the possibility that they were seeing two separate radio galaxies aligned by chance, and model the jet's interaction with the intergalactic medium to understand their physical properties. This required combining data from optical telescopes like the Sloan Digital Sky Survey, which had catalogued the host galaxy's position and basic properties, with the radio observations from LOFAR, and then adding information from X-ray observatories and infrared telescopes to build up a complete picture. Modern astronomy is fundamentally a multi-wavelength endeavor. No single telescope or wavelength band tells the whole story. You need to observe the same object across the electromagnetic spectrum, from radio waves through microwaves, infrared, visible light, ultraviolet, X-rays, and even gamma rays, to fully understand what's happening. Each wavelength reveals different physics. Radio observations show us the synchrotron radiation from relativistic electrons spiraling in magnetic fields. Infrared observations reveal dust heated by star formation or black hole activity. Optical light shows us stars and ionized gas. X-rays highlight extremely hot gas and high-energy processes near black holes. By combining all these perspectives, we can piece together the full story of what's happening in these extreme cosmic environments. The host galaxy of Porphyrion, when observed in optical wavelengths, appears as a relatively normal massive elliptical galaxy. These are the galactic senior citizens, large red spheroidal collections of old stars with very little ongoing star formation. They've already converted most of their available gas into stars and settled into a quiet retirement, but appearances can be deceiving. Deep in the core of this seemingly tranquil galaxy sits a supermassive black hole containing billions of solar masses actively consuming matter and launching jets that span a significant fraction of the distance between galaxy clusters. This dichotomy between the peaceful-looking galaxy and the violent activity in its core illustrates something profound about the universe. Extreme phenomena often hide within ordinary-looking objects. The most powerful explosions in the universe, gamma-ray bursts, come from stars that look unremarkable until the moment they die catastrophically. Supermassive black holes capable of devouring entire star systems lurk in the centers of galaxies that appear placid and stable. The lesson here is that you can't judge a cosmic object by its superficial appearance. You need to look deeper, across multiple wavelengths and with multiple instruments, to understand what's really going on. Let's talk about the future of this field, because we're entering a golden age of radio astronomy. LOFAR is just the beginning. The Square Kilometre Array, or SKA, currently under construction, will dwarf LOFAR in collecting area and sensitivity. When completed, the SKA will consist of thousands of antennas spread across South Africa and Australia, with a total collecting area approaching 1 square kilometre, hence the name. It will be 50 times more sensitive than any existing radio telescope and will survey the sky 10,000 times faster than current facilities. With the SKA, we'll be able to detect radio galaxies at much greater distances, looking back to earlier epochs of cosmic history. We'll find jets that are even larger than Porphyrion, or will establish firm upper limits on how large these structures can actually grow. We'll study the evolution of radio galaxy populations across cosmic time, understanding how black hole activity has changed as the universe aged. We'll map the magnetic fields of the cosmic web with unprecedented detail, tracing the fingerprints left by generations of radio galaxies. The SKA will also help us understand the connection between radio galaxies and their cosmic environment. Do giant radio galaxies preferentially exist in certain types of environments? Do they form more readily in cosmic voids where the intergalactic medium is less dense, allowing jets to propagate further? Or do they need the dense environments of galaxy clusters to trigger the black hole activity that powers the jets? These questions have different answers depending on which theoretical model you prefer, and observational data from the SKA should finally let us distinguish between competing theories. Beyond radio astronomy, upcoming optical and infrared surveys will also contribute to this field. The Vera Rubin Observatory, currently in its final stages of construction in Chile, will conduct the Legacy Survey of Space and Time, or LSST, imaging the entire visible sky every few nights for 10 years. This will create an unprecedented database of how the universe changes over time, capturing everything from asteroids in our solar system to distant supernovae and actively feeding black holes. By correlating Rubin Observatory data with radio surveys, astronomers will be able to study the connection between optical properties of galaxies and their radio emission in unprecedented detail. The European Space Agency's Euclid mission, launched in 2023, is mapping the large-scale structure of the universe with exquisite precision, measuring the positions and shapes of billions of galaxies. This data will help us understand the cosmic web in which giant radio galaxies exist, showing how matter is distributed on the largest scales and how structures like Porphyrion's jets fit into that cosmic architecture. NASA's James Webb Space Telescope, already delivering breathtaking images and spectra from the early universe, will help us understand the host galaxies of distant radio sources, revealing details about their stellar populations, star formation histories, and black hole properties. All these facilities working together will give us an unprecedented view of how supermassive black holes, their host galaxies, and the cosmic web interact and co-evolve. We're moving from an era where discovering a single giant radio galaxy was noteworthy to an era where we'll have statistical samples of thousands of these objects across cosmic history. This transition from case studies to population statistics is how astronomy matures as a science, moving from cataloging curiosities to understanding fundamental processes. But even with all these technological marvels, there are limits to what we can observe. Radio waves, like all electromagnetic radiation, travel at the speed of light. The most distant objects we can ever hope to see had their light emitted when the universe was very young, and as the universe continues to expand, fewer and fewer of these distant objects will remain observable. In the far future, billions of years from now, the expansion of space will have carried distant galaxies beyond our cosmic horizon. Civilizations arising in that distant epoch will look out at a much emptier universe, with only their local group of gravitationally bound galaxies visible. The evidence for the Big Bang and cosmic expansion will be much harder to come by. They might even conclude they live in a static, eternal universe, unaware of the vaster cosmos that exists beyond their reach. We're fortunate to live in an era where the universe is old enough to have developed complexity and structure, yet young enough that we can still observe a significant fraction of cosmic history. We can look back to within a few 100 million years of the Big Bang and see the first galaxies forming. We can observe cosmic noon when star formation peaked. We can study the present epoch where the universe is settling into a more sedate middle age. And we can use the laws of physics to project forward, understanding how the cosmos will evolve over the coming billions and trillions of years. This cosmic perspective, this ability to situate ourselves within the full sweep of cosmic history, is one of humanity's greatest intellectual achievements. For most of human history, people believed the universe was essentially static and eternal, or at most a few thousand years old. The realization that we inhabit an evolving cosmos with a definite beginning and a predictable future, that we can trace cosmic evolution from the Big Bang through the formation of stars and galaxies to the present day and beyond, represents a profound shift in human understanding. Discoveries like Porphyrion contribute to this grand narrative. They show us that even in today's relatively quiet universe, extraordinary things are happening. They remind us that supermassive black holes aren't just exotic objects to study in isolation, but active participants in cosmic evolution, shaping their environments on scales that boggle the mind. They demonstrate that the universe still has surprises in store, that our models and theories, while impressive, remain incomplete. Let me share another mind-bending aspect of these observations. When we look at Porphyrion, we're seeing light that has been traveling through space for 7.5 billion years. Earth didn't exist when that light began its journey. Our solar system was still a diffuse cloud of gas and dust, decades away from beginning the collapse that would eventually form the Sun and planets. The light from Porphyrion traveled through expanding space, riding the cosmic expansion, gradually shifting to longer and longer wavelengths as the universe stretched. Along the way, that light passed through galaxy clusters, cosmic voids, and dense filaments of the cosmic web. Some of it was absorbed by intervening gas clouds, creating absorption lines that astronomers can study to learn about the intergalactic medium at various epochs. Some of it was gravitationally lensed by massive galaxies, bent and distorted by the curvature of space-time around concentrations of matter. The photons we eventually detect with LOFAR are survivors, representatives of a much larger population that was emitted 7.5 billion years ago. And here's something that really drives home the strangeness of cosmic distances and timescales. By the time this light reaches us, the source has moved. Due to cosmic expansion, Porphyrion is now about 10 billion light-years away, even though the light took only 7.5 billion years to reach us. If we could somehow instantly teleport to where we see Porphyrion in the sky, we wouldn't find it there. We'd arrive at a point in space where Porphyrion was 7.5 billion years ago. To find it as it exists in the present moment, we'd have to travel much further, to where it's being carried by cosmic expansion. Of course, there's no such thing as the present moment for an object billions of light-years away. Relativity tells us that simultaneity is relative, that there's no absolute cosmic time that applies everywhere in the universe. When we say Porphyrion as it exists now, we're really talking about a theoretical construct, not something we can directly observe. All we can ever see is the past, the light that has had time to travel from there to here. The universe is, in a very real sense, a time machine, constantly showing us the history of the cosmos written in light from distant objects. This raises a fascinating question that cosmologists sometimes ponder. If we had powerful enough telescopes and could look far enough across the curved geometry of the universe, could we theoretically see all the way around and observe our own galaxy from the other side, seeing ourselves as we were billions of years ago? The answer, disappointingly, is no. The universe isn't old enough, and space isn't curved in quite the right way. But it's a fun thought experiment that illustrates just how strange and counterintuitive cosmology can be. Back to Porphyrion and its implications. One of the reasons this discovery is so significant is that it helps us understand the topology of energy distribution in the universe. Energy isn't uniformly distributed. It's concentrated in certain places like stars and black holes, while vast voids contain almost nothing. But structures like Porphyrion's jets redistribute energy from these concentrated sources across enormous volumes of space. They're cosmic energy transport mechanisms, taking energy that would otherwise be locked up in the gravitational potential well of a black hole and spreading it across megaparsecs of intergalactic space. This energy redistribution has consequences. The intergalactic medium heated by jets like these becomes less likely to fragment and collapse to form new galaxies. The pressure support from this heated gas can stabilize structures against gravitational collapse. The magnetic fields carried by the jets can affect how gas clouds interact and merge. In subtle ways that we're only beginning to understand, The activity of supermassive black holes billions of years ago shaped the distribution of matter and energy in the universe we observe today. There's also the question of feedback loops and self-regulation. When a supermassive black hole launches powerful jets that heat the surrounding gas, it's effectively cutting off its own fuel supply. Hot gas has too much pressure support to fall into the black hole, so the accretion rate drops, the jets weaken, and eventually the activity ceases. The gas then cools over millions of years, begins to fall back toward the center, reignites black hole activity, and the cycle repeats. This creates a self-regulating system where black holes alternate between active and quiescent phases. Giant radio galaxies like Porphyrion represent a particular phase in this cycle, likely one where conditions were just right for sustained jet activity over exceptionally long periods. Perhaps the black hole had accumulated an unusually large reservoir of fuel. Perhaps the surrounding environment was particularly conducive to jet propagation, with low-density gas allowing the jets to travel further before dissipating. Perhaps the black hole's spin and the geometry of the accretion disk were optimally aligned to produce particularly stable, powerful jets. Distinguishing between these possibilities requires detailed modeling and more observations. What happens to Porphyrion now? Well, now is a complicated concept across cosmic distances, as we've discussed, but let's consider the galaxy as it exists in its own reference frame, approximately 13 billion years after the Big Bang in cosmic time. The jets might still be active, continuing to pump energy into the intergalactic medium, or they might have shut off sometime in the intervening 7.5 billion years since the light we observe was emitted. If we could observe Porphyrion as it exists in the present cosmic epoch, we might see something completely different, a quiet elliptical galaxy with fading radio lobes, or perhaps an entirely new episode of activity with jets pointing in a different direction. This touches on another fascinating aspect of radio galaxies. Orientation matters tremendously. When we observe a radio galaxy like Porphyrion from the side, we see both jets and lobes clearly, and we can measure their full extent. But if we happen to be looking down the barrel of one of the jets, we'd see something completely different. The jet pointing toward us would be dramatically brightened by relativistic beaming, an effect where the Doppler shift and special relativity combine to make material moving toward you appear much brighter than material moving away. When a radio galaxy is oriented with one jet pointing nearly directly at Earth, we call it a blazar, and it appears as an extremely bright variable radio and gamma-ray source. The other jet pointing away from us becomes almost invisible due to relativistic de-beaming. If Porphyrion were oriented this way, we would never have discovered its true size. We'd see a bright blazer and have no idea that behind it stretches a 23 million light-year structure. Orientation is destiny in observational astronomy. What you see depends critically on your viewing angle. This means that for every giant radio galaxy we discover, with jets oriented favorably for observation, there are others that we're missing because they're oriented edge-on or at unfavorable angles. Statistical models try to account for these orientation biases, correcting our observed samples to estimate the true underlying population. These corrections suggest that giant radio galaxies might be several times more common than our raw counts indicate, though they're still rare compared to normal galaxies. Let's consider the human element in these discoveries for a moment. Behind every astronomical breakthrough are people, students staying up late processing data, postdocs developing new analysis algorithms, senior scientists designing surveys and writing proposals for telescope time, engineers building and maintaining the instruments, software developers creating the tools that make modern data analysis possible. The discovery of Porphyrion represents thousands of hours of human effort, built on foundations laid by previous generations of astronomers and physicists. Martijn Oe, the lead author on the Porphyrion discovery paper, was a PhD student when he found this system. Think about that. A graduate student, probably in their mid-20s, sifting through data, developing new techniques, and ultimately discovering the largest known galactic structure. This is one of the beautiful aspects of modern science. Important discoveries can come from anyone willing to put in the work, regardless of their position in the academic hierarchy. Yes, senior scientists with decades of experience contribute crucial insights and guidance, but the actual work of discovery often falls to younger researchers, bringing fresh perspectives and new skills. The collaborative nature of modern astronomy also deserves recognition. The Porphyrion Discovery paper lists multiple authors from different institutions across several countries. This is typical of contemporary astronomical research. The days of lone astronomers making discoveries in isolation are largely gone. Today's astronomy requires teams with diverse expertise, observers who know how to extract maximum information from telescopes, theorists who can model complex physical processes, data scientists who can handle massive data sets, and specialists in particular wavelength regimes or object types. International collaboration is essential because the best telescopes are spread across the globe, and no single institution or country can maintain expertise in all necessary areas. LOFAR, the telescope that made these discoveries possible, is itself an international facility with stations in the Netherlands, Germany, Poland, France, Sweden, the United Kingdom, Ireland, and Latvia. Data flows freely between institutions with agreements ensuring that after proprietary periods, observations become publicly available for anyone to analyze. This open data philosophy has accelerated discovery tremendously. Alcyoneus, the previous record holder for largest galaxy, was discovered by reanalyzing publicly available LOFAR data. The data had been released by the original observers, and a different team, using different techniques, found something the initial analysis had missed. This is increasingly common in astronomy. We're drowning in data, and there's simply no way that the original observers can extract every piece of information from their data sets. Making data public allows the broader community to contribute, essentially crowdsourcing the analysis across the global astronomical community. Looking forward, the volume of publicly available astronomical data will continue to grow exponentially. The legacy survey of space and time from the Vera Rubin Observatory will generate approximately 20 terabytes of data every night for 10 years. The Square Kilometre Array will produce exabytes of data annually, more than the entire global internet traffic today. Managing, distributing, and analyzing these datasets will require infrastructure and computational resources on par with what's used in particle physics experiments like the Large Hadron Collider. This data deluge presents both challenges and opportunities. The challenge is developing algorithms sophisticated enough to sift through billions of objects and identify the rare, interesting cases worth detailed follow-up. Machine learning and artificial intelligence are increasingly essential tools for this task. Algorithms can be trained to recognize patterns associated with particular types of objects, flagging candidates for human review. But there's a catch. Machine learning algorithms are only as good as their training data, and they're notoriously bad at finding things they haven't been trained to recognize. The weirdest, most unexpected discoveries might slip through automated filters designed to find objects that match our preconceptions. This creates a tension in modern astronomy between efficiency and serendipity. We need automated systems to handle the data volume, but we also need human eyes and human intuition to spot the unexpected. Striking the right balance is an ongoing challenge. Some surveys dedicate a fraction of their analysis pipeline to specifically look for outliers and anomalies, things that don't fit neatly into established categories. These are often the most scientifically interesting objects because they challenge our theories and force us to expand our understanding. Porphyrion itself might have been one of these outliers. When the analysis software flagged a radio source extending over such enormous angular scale, it might have seemed like an error at first. Instrumental artifacts, data processing glitches, and random alignments of unrelated sources can all create false positives. Distinguishing genuine discoveries from spurious detections requires careful validation, cross-referencing with other datasets, and often follow-up observations with different instruments. The fact that we now have multiple examples of galaxies with jets exceeding 20 million light-years confirms that these aren't flukes but a genuine, if rare, population of objects. The philosophical implications of these discoveries extend beyond astronomy. They remind us of the provisional nature of human knowledge. Each generation thinks it has roughly figured out how the universe works, and each generation discovers phenomena that force revision of those models. Before LOFAR and similar sensitive low-frequency radio telescopes, we had no idea that structures like Porphyrion existed. They weren't predicted by theory. No one was specifically looking for them. They emerged from the data as a surprise, forcing us to rethink our models of jet propagation, intergalactic medium properties, and black hole activity. This pattern repeats throughout the history of science. New instruments with new capabilities reveal phenomena that were previously invisible, and these discoveries necessitate conceptual revolutions. Galileo's telescope revealed moons orbiting Jupiter, demonstrating that not everything orbits Earth. Spectroscopy revealed that stars are made of the same elements found on Earth, establishing the universality of physical law. Radio telescopes discovered pulsars, quasars, and the cosmic microwave background. Each advance in observational capability has reshaped our understanding of the cosmos. What will the next generation of instruments reveal? What phenomena currently lie beyond our observational reach, waiting to surprise and perplex future astronomers? We can make educated guesses based on theoretical predictions, but history suggests that the most important discoveries will be the ones we didn't anticipate. This is why investment in observational astronomy remains crucial. We're not just building better telescopes to answer existing questions, we're creating the tools that will reveal questions we don't yet know to ask. Let's return to the cosmic web for a moment, because Porphyrion's relationship with this larger-scale structure deserves more attention. The cosmic web isn't just a metaphor, it's a real physical structure that you could, in principle, navigate. If you were an impossibly patient traveler capable of moving between galaxies, you would find that galaxies are organized into groups and clusters connected by filaments, with vast voids in between. Following a filament, you'd pass galaxy after galaxy, strung along the thread like beads on a string, venture off into a void, and you'd travel for hundreds of millions of light-years encountering almost nothing. Porphyrion's jets, stretching 23 million light-years, span a significant fraction of the typical spacing between filaments. In some regions of the universe, these jets might reach from one filament to an adjacent one, creating a bridge not just of radio emission, but of energy, magnetic fields, and heated plasma. They're physically connecting different strands of the cosmic web, transferring energy and magnetic flux between structures that might otherwise be causally disconnected on these enormous scales. This raises the intriguing possibility that radio galaxy jets serve as a mechanism for communicating information across the cosmic web. Not information in the sense of signals or messages, but physical information about magnetic field orientation, energy distribution, and plasma conditions. When jets from one galaxy inject energy and magnetism into a filament, they affect the conditions in that filament, which in turn affects other galaxies embedded in it. This creates a web not just of matter, but of influence, where the activity of supermassive black holes can have downstream effects on structures millions of light-years away. Some theoretical work suggests that the magnetic fields of the cosmic web might have been seeded by jets from the first generation of radio galaxies in the early universe. Before that, the intergalactic medium might have been essentially devoid of magnetic fields, But once the first black holes began launching jets, they injected magnetic fields into the surrounding space. These fields were then stretched and amplified by the expansion of the universe and by turbulent motions in the intergalactic medium, eventually creating the large-scale magnetic field structures we observe today. If this picture is correct, then every time we observe a giant radio galaxy, we're not just seeing an individual object, but witnessing a process that has shaped the electromagnetic environment of the entire universe. The collective action of millions of radio galaxies over billions of years has magnetized the cosmos, creating fields that now permeate intergalactic space and influence everything from galaxy formation to the propagation of cosmic rays. Cosmic rays, speaking of which, are another piece of this puzzle. These are high-energy particles, mostly protons and atomic nuclei, that zip through space at nearly the speed of light. When they strike Earth's atmosphere, they create cascades of secondary particles that can be detected by ground-based observatories. The origin of the most energetic cosmic rays remains one of the great unsolved problems in astrophysics. They carry so much energy that few astrophysical processes seem capable of accelerating them to such speeds. Radio galaxy jets are among the prime candidates for ultra-high energy cosmic ray acceleration. The shocks and turbulence in these jets can act like enormous particle accelerators, boosting particles to energies that dwarf anything we can achieve in terrestrial labs like the Large Hadron Collider. If this is correct, then somewhere in the universe right now, a particle is being accelerated in the jets of a radio galaxy like Porphyrion, eventually to be flung into intergalactic space where it will wander for millions of years before perhaps, by chance, striking Earth's atmosphere and being detected as an ultra-high energy cosmic ray. The connection between radio galaxies and cosmic rays illustrates a broader theme. The universe is deeply interconnected. Nothing exists in isolation. The activity of a black hole 7.5 billion light-years away can, through a chain of physical processes, affect conditions in our local neighborhood. The particles that make up your body were forged in stars that exploded billions of years ago, scattering their enriched material into space, where it eventually coalesced into new stars and planets. The atoms in your left hand might have originated in a different star than the atoms in your right hand. We are, quite literally, made of stardust, and the processes we observe in distant galaxies like Porphyrion are part of the same cosmic cycle of matter and energy that created everything around us. This cosmic perspective has a way of making everyday concerns seem small, but it also has the opposite effect. It makes us, as conscious observers, capable of understanding these processes, seem rather remarkable. The universe has existed for nearly 14 billion years. For most of that time, it consisted of mindless matter, following physical laws. Then, at least on one small rocky planet orbiting an unremarkable star, matter organized itself into structures complex enough to become aware, to wonder, to ask questions and seek answers. We are the universe contemplating itself, local concentrations of complexity that have emerged from the cosmic evolution we're describing. The fact that we can look across billions of light years and understand what we're seeing, that we can decipher the physics of black holes and jets and intergalactic plasma, represents something profound. The laws of physics are universal. The same quantum mechanics and general relativity that govern events in Porphyrion also govern events in your backyard. By studying extreme phenomena in distant galaxies, we're learning about the fundamental rules that govern all of reality. And by extension, we're learning about ourselves and our place in the cosmos. Looking ahead, the study of giant radio galaxies is poised for rapid advancement. The combination of larger surveys, more sensitive instruments, better computational tools, and growing international collaboration means we'll discover and characterize many more of these systems in the coming years. Each new discovery will refine our understanding of how common they are under what conditions they form, and how they impact their environments. We'll build statistical samples large enough to test theoretical predictions about jet physics, black hole demographics, and cosmic feedback. We'll also develop better simulations. Modern cosmological simulations can model the evolution of the universe from shortly after the Big Bang to the present day, following the growth of cosmic structure across billions of years and billions of light-years of space. These simulations increasingly include sophisticated models of black hole activity and jet feedback. As our understanding improves, these simulations will become more accurate, allowing us to make predictions that can be tested against observations. The interplay between simulation and observation drives progress in cosmology, with each informing and constraining the other. There's something almost poetic about the fact that the largest structures associated with individual galaxies are created by the smallest and densest objects in the universe, black hole. The event horizon of even a supermassive black hole containing billions of solar masses is only about as large as our solar system. Yet the influence of that tiny, dense object extends across 23 million light-years, spanning a good fraction of the distance between galaxy clusters. It's a testament to how profoundly gravity and magnetism can organize matter and energy across vast cosmic scales. As we close this exploration of Porphyrion and the giant radio galaxies, it's worth reflecting on what these discoveries mean for the future of astronomy. We're entering an era where we'll map the universe in unprecedented detail, cataloging billions of galaxies, tracing the cosmic web across cosmic time, understanding how structures at every scale form and evolve. The picture that emerges will be immensely complex, far more intricate than the simplified models we've relied on until now. But from that complexity will come deeper understanding. We'll understand how the first stars and galaxies formed in the early universe. We'll trace the co-evolution of black holes and galaxies across cosmic history. We'll map the distribution of dark matter and dark energy, those mysterious components that make up 95% of the universe but remain poorly understood. We'll watch as the universe continues to expand and evolve, ultimately projecting forward to its ultimate fate trillions of years hence. And through it all, structures like Porphyrion will serve as reminders that the universe still has the capacity to surprise us. Just when we think we understand the typical scales and energies involved in cosmic phenomena, nature reveals something even more extreme. The largest known galaxy today might be superseded tomorrow by an even larger discovery. The most powerful jets we've observed might be dwarfed by future findings. This is the nature of frontier science. The boundary of knowledge is always moving, and beyond it lies territory we've barely begun to explore. For those of us fascinated by these questions about cosmic scale, about our place in the universe, about the fundamental nature of space, time, matter, and energy, this is an exciting time to be alive. We have the instruments, the computational power, and the theoretical frameworks to address questions that previous generations could only dream about. And with each answer comes new questions, deeper and more profound than what came before. The discovery of Porphyrion, with its 23 million light-year jets connecting the cosmic web, represents a milestone in this ongoing journey of discovery. It shows us that even in the present-day universe, extraordinary processes are unfolding. It demonstrates the power of modern astronomical instruments to reveal phenomena that were previously invisible. And it hints at a universe that is richer, more complex, and more interconnected than we ever imagined. Make sure to give this video a like and subscribe to the channel if you made this far. Your help is the biggest fuel to keep this channel going. And if you're curious about the layers of motion we experience, from Earth's rotation to our solar system's orbit, our galaxy's movement, and our journey through the expanding cosmos, make sure to check the video at the left side of the screen. where we explore the mind-bending reality of our motion through the universe. See you there.